Hello, my name is Alejandro Gonzalez Flores. I'm a master's student in chemical engineering at Texas Tech University, and today I will be presenting a Simplex method, which is a method in linear programming optimization. First, I would like to give a little background about the method. As I was mentioning, it's an algorithm for linear programming, which was published by George Bernard Datskin in 1947. It has been considered by many journals as one of the top 10 algorithms in the 20th century, and its name it's derived from the complex of simplex in geometry, which is a generalization of the notion of a triangle or a tetrahedron in arbitrary dimensions. The simplex method is a optimization method that is designed to solve a specific kind of problems. In this case, both the objective function and the constraints must be linear and satisfying a linear programming standard form. Both the function and the constraints must be weight sums of the decision variables, and the constraints, if they are inequalities, they should be converted into equalities by the addition of slack variables. As you can see, here's an example of a maximization problem where the first line, it's the objective function z equals to 2x1 plus 1.5x2, subject to two different constraints. These constraints would have to be converted to equalities in order to make the method work. Different optimization methods work in different ways. Some move in the direction of the gradient and step size is variable, while some other methods move in a deflection of the gradient, and there are some other methods that move in the direction that it's composed of both the Hessian and the gradient of the function. In the case of the simplex method, the method must move in a direction that improves the objective function at each iteration. To check if the direction improves, we do a dot product with the objective function and look at the sign of the results. The step size, as compared to other methods, only has a limit if the movement violates a non-negative constraint. Now that we have an idea of how the method works, let's look at the real-world problem and go through each of the steps of the simplex algorithm. Before solving using simplex method, we will look at how a simple problem can be solved graphically. However, as the problem is more complex and with more variables, we need a systematic way of solving, which would be simplex. Now, for our example problem, let's consider a company that produces two different products. The first product can be sold at $200 and the second at $150. The budget on buying the most important part for each of the products is $2,500. The part for the first product costs $7.50, and the part for the second product costs $10. The maximum allotted time for production is 1,200 hours total. It takes 6 hours to make the first product and 3 hours to make the second. Our goal is to maximize the revenue in this production. We can mathematically rewrite our problem by writing an objective function. In our case, we have our objective function based on the revenue. Then we have our constraints. In our case, our first constraint is based on the budget to buy the parts for the product, and the second constraint would be based on the allotted time to produce each of the products. If we were to solve graphically, we would have to plot the constraints and find the feasible region. In this case, it will be the region enclosed by point 1, 2, and 3 and the origin. Then we enumerate the points that are corners in our feasible region. In this case, number 1, 2, and 3. Then we will have to evaluate our objective function at each of these points to see which one gives a a best value for our objective function. By doing this, we find that in our case, our optimum is at point 2, where we find that there's 120 units of product 1 and 160 units of product 2, giving us a revenue of $48,000. In order to solve with Simplex method, we have to rewrite our objective function and constraints to get rid of the inequalities in the constraints. In order to do this, we will have to add slack variables. In this case, our slack variables would be S1 and S2. The easiest way to solve a Simplex problem is by creating a table. In this table, the first row that you can see circled in red are the coefficients of the objective function. Then we have a column for the basic variables for each of the variables in the constraints, and what we have at the right side of the constraint, and then a value that will be calculated as theta. First, we select as basic variables. The easiest thing is to select our slack variables. To the left of them, we write the coefficient that are present in the objective function, as you can see circled in red for the two zeros. Then, for x1, in the column for x1, we write the coefficients for the constraint, and the same for x2, S1 and S2. Then we write the value at the right side of the constraint. The last row, it's the iteration where we calculate Cj minus Zj. In this case, to calculate Zj and Cj minus Zj, we do dot product of the coefficients of the constraints with the coefficients of the objective function. And as you can see, there's the calculation for each of the variables, and we get 100, 150, 0, 0, and 0. From this row, we have to select the maximum value. In this case, you can see that the maximum value for iteration 1 is 200. Then we have to divide each of the values for the right side column by the coefficients in the column with the maximum value for the iteration. In this case, we will have 2500 divided by 7.5 and 1200 divided by 6. This will give you a value of 333.33 for the first theta and 200 for the second theta. From the values of theta, we have to select the minimum value, and by looking at what the maximum value in the last row and the minimum value at the theta column, we will know which basic variable will be leaving and which variable will become a basic variable in order to improve our next iteration. From these values, we can see that the variable S2 will be leaving the basic variables, and the variable x1 will become a basic variable. Then we continue to construct the table by adding some more rows where we have our new basic variables with their coefficients to the left. Our goal will be to have an identity matrix for our basic variables. Since we left S1 as one of our basic variables, we leave that column untouched, but our variable x1 will have to become a column with 0, 1 as it was S2 before. So in order to do this, we have to create a matrix with the coefficients of the constraints and the right side of the constraints, and perform row operations in order to get the matrix with the identity matrix for those basic variables. And we can see that after performing the row operations, we get the matrix from the first matrix to the second matrix, where we have 0 and 1 for the variable x1 and 1 and 0 for the variable s1. If we continue to do the same procedure for each of the iterations, we'd see that at iteration number 3 we get negative values for all the negative values or 0 for all the values of cj minus dj. At this point we stop our algorithm and find out that our maximum value is 48,000 and our optimal values for x1 and x2 it's 120 and 160 respectively. Convergence occurs in finite time and it scales to the number of vertices or intersections in the simplex figure formed by the intersection of the constraints. Some applications involve industrial decisions, medicine, marketing, and even chemical engineering or reactions.